Dr. Saab, I hope my voice is clear enough and my screen is visible.
Ji, we can hear and
All
see.
right, right. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي. All right, I welcome all of you to this session. So, in this session, we will be going through this specific topic on knowledge based engineering. Um, so, I assume that this term, knowledge based engineering or KBE, as it is known in the industry, some of you might have heard it, for some, it might be new. So, let's go through from the beginning and see how it is uh, playing a key part in the product development uh, life cycle of today's industry. So for the agenda, we'll have the introduction of the topic, overview of KBE, knowledge-based engineering. It's known as KBE popularly. Some applications and case studies, uh, and then some technology landscape and career prospects. What skills one needs to make a career in KBE and to progress in KBE. Also, we'll have some discussions on career transition. Who can be a part of this KBE processes, KBE ecosystem, and then we'll have some summary, and of course we'll have questions at the end if you have. So we'll take up the questions at the end of the presentation, inshallah. So please note down your questions, or you can put it in the chat box. We can take it up in the end. So Jeff Imlet says, if you went to bed last night as an industrial company, you're going to wake up today as a software and analytics company. This is he said this around 4 years back. Jeff Imlet was the CEO of General Electric, and this statement is all the more relevant in today's age, where we see software and analytics and data sciences, machine learning taking over every aspect of not only the engineering industry but every aspect of life. So naturally, even the engineering industry, the hardcore engineering industry, is evolving according to this paradigm shift. So we have these new age technologies touching the legacy engineering fields, be it civil engineering, be it mechanical engineering, be it electrical engineering, be it material science, metallurgical engineering. So everybody is taking a step towards being a software driven company, uh, rather than being a purely hardware driven company. So this is a paradigm shift what he anticipated few years back, and this is gaining relevance and importance all the more in today's age. And the companies are making their strategic decisions and their investments in this direction. you know a few facts about the industry, basically, which led to the eruption of this field of product development called KBE. KBE is nothing new. It's not independent technology per se, but it is a way to make your traditional product development more and more uh, efficient, uh, more cost effective, and more faster time to market. All right, so these are the few facts of the industry which led to the formation of this KBE as an independent field of its own. Human resource is the greatest resource of any organization. It is because of the knowledge and the skills what the human beings which who are part of that organization possess. So it's really imperative and it's really important to capture that knowledge and to also reuse that knowledge. And this process of capturing the knowledge and reusing the knowledge, what humans have, because the people who run the company are human beings, and it is because of the skills and the knowledge and the know-how that a company is built and a company is run, and that's what defines the success of the company. uh, we should have structured process to capture and reuse the knowledge uh, of the people of the company. And so this process of capturing and reusing the knowledge should be very structured in organization. And also, we know that the time of an engineer is really valuable, and it has to be used for engineering tasks. As in how we progress in the industry, sometimes we end up doing redundant tasks, the tasks which we have been doing over the years. So it gets boring, but and that leads to loss of efficiency in the people, and that again it leads to it directly affects the financials of the company and the results of the company. So a company has always to be in the competitive market. We know how competitive the market is. Uh, you have to continuously keep upgrading yourself. You have to keep innovating within the company. You have to come up with new ideas, new things, in order to stay afloat, in order to survive, in order to stay relevant in the industry. And it's all about time, and the time which has to be used for creative works has to be maximized, and the time which has to be used for routine and redundant works has to be optimized or minimized. I will not tell minimized, because that has to be done in order to keep the company running, but it has to be optimized. You should not spend a lot of time in doing routine and redundant works. And in increasing the efficiency, even a small gain of productivity, um, when it is multiplied with a large user base, it will yield a huge result for the company. For example, you come up with a process. You come up with a process from the product development perspective. I'm telling, for a design engineer, you come up with a new tool or a process which can save 1 minute of one design engineer. 1 minute of one design engineers. And big companies have thousands of design engineers. So if you multiply that 1 minute with that large user base of thousands of people, it will save thousands of minutes, and that again will help the company save that much of cost. And we all know this, that in the early design stage, if we detect the quality faults and quality defects and take measures to improve it and take measures to address it, so that will help in the product development phase itself. And in comparison to detecting the quality defect at the production stage, wherein we would have finished all the, finalizing the designs, beginning with the prototypes, and also beginning the production at a mass level, at identifying defects at that time is really costly, and it costs a lot to the company in terms of everything, in terms of manpower, in terms of cost, in terms of time, in terms of the competition in the market also, right? So in order to prevent all this, it's always good to detect a quality defect and a design defect at the stage of the design itself. So again, to help in all these points, we have KBE which kicks in. And of course, we all know about the time to market. We all speak about the time to market. So that gives the companies a competitive edge over the competitors, right? A monopoly or the competitive edge over the competitors is obtained by the time to market. The faster the product comes to market, the better the results for the company are, right? So all these 5 points are the basis for which this topic of knowledge based engineering was evolved. It started out initially as a part of the traditional product development life cycle, but then as it sort of matured over the years, it separated out into a different vertical sort of vertical. And then it helps in the product development life cycle of each organization. So what are the typical knowledge problems? So see, every company runs on the knowledge, and knowledge comes with its own problems. If you see in legacy companies, knowledge is more sort of disorganized. you know um, Around 4 years back, I used to work for a Swedish company. So there, they had their knowledge base of around 45 years. They had their codes, their design tables, and that was, their design code. It was programmed in Fortran, which was completely disorganized. It was not object oriented, and the people who had written that code for design, based on which their whole product design was happening. There was a code, and their whole product design was happening because of their code, because of that code. But the problem was these people who are part of this company did not know how that code works. And it's a big company. This actually happens in big companies because the people who had written that code had either had retired from the company or they had left the company. So that code was disorganized, and that was the basis on which their products were designed for many many years. So it's disorganized. It's insecure also. As I told, people who work on a specific domain, they don't work in the company forever. They either retire or they shift their roles. They even shift their teams. This happens a lot in companies also. uh, एक तो you shift your company, you shift from company A to company B. So the entire knowledge, it goes away from the person when he shifts a company, when he leaves a company. Also, when a person changes teams also, a- within the same company, a person changes from team A to team B. Even when he goes to a different team, he will not have time, he will not have the resources, he will not have the bandwidth to support his earlier role. So in that case also, the knowledge goes away with him. So the knowledge is insecure, it's volatile also. Knowledge is volatile. It's not stable. It's not stable, and it's sometimes excessive. You have so much of data, you have so much of especially this problem arises in old companies which have been which have been around for 60 years, 70 years, 80 years, 100 years. A lot of companies who are into this traditional product development, they have huge knowledge. They have their own physics, they have created their own physics, built up their own physics. They have their own science, they have their own equations. So it's a lot of knowledge, and sometimes the people who work today, they don't know how to make sense out of that knowledge. So knowledge based engineering aims to encapsulate all these problems into a structured system, and it aims to address these problems and aims to minimize the difficulties arising from these problems. Now, what is KBE? There is no one definition of KBE. All right. If you look around on the internet, first of all, you'll find a sort of very less literature on what this actually is. We have a few research papers who have come up with definitions. So we have got multiple definitions from multiple perspectives. Okay, some people tell it's a computer system to aid the product development process, and it it takes place of domain specialists, the people who know the domain, who are experts of that domain. It minimizes their job, or rather it eases their job. It eases that this It's a computer system, KPE, which helps in the creation of products to ease the job of human experts. This is one definition from a perspective. Some people also tell it's a means by which the processes of the company can be translated into software. Every company has its huge processes, has its own processes. A person who shifts a company, who moves to a new company, it takes 2, 3, 4 months to just understand the processes of the company. Although the technology is same, although the domain is same, each company has its own custom processes. So to translate those processes into softwares and to ultimately save money and time, in order to have a good engineering and a manufacturing scale, is what KBE is all about. Now these questions typically come to our mind. So if you tell if it's a computer system, so will it replace the domain experts? Will there be no need of human beings, is the question which comes to the people who are into traditional product development, traditional CAD, traditional drafting, traditional simulations. So will it take away the jobs? The answer is no. Absolutely no. As I told in the beginning also, it eases the jobs of the domain experts. We did not have calculator. Calculator came in and it eased the job. People have to upgrade and upskill themselves to adapt to the calculator. In the same way, this is a way of product development to which, if it is adapted, it will ease the job of domain experts. Again, when you tell companies processes can be translated to a software, will it mean that a computer will run our company better than we can? Again, the answer is no. The computer is there to improve your efficiency, your time, and to help avoid errors, to improve your accuracy. Now, a bit of history from where it came from. It all started when the word AI, artificial intelligence, was introduced. Decades ago. A computer software which does not only solve the regular problem, whatever you program, but it is intelligent enough. It is intelligent enough to learn from mistakes, apply common sense from the previous data, from the previous knowledge, to solve the problems which are not explicitly programmed. One program, we know what is explicitly programmed. Whatever you program, according to that you give results. They tell garbage in, garbage out, right? So that is one kind of the traditional programming what we have. AI does not do that. It learns from its previous knowledge. It has algorithms to learn, to train itself, and then to predict the results for the data which is not explicitly programmed. So when this AI came into the market, the traditional product development people who used to design, who are into the design of sort of mechanical components. It can be automobile, pistons, engines, crankshaft, safety systems, all the automobile components, all the traditional. It can be machinery. We have bearings, we have nuts, bolts. As simple as that. As simple as that. So these people who are into this traditional product development, they started to think of ways to employ artificial intelligence to address their design problems. So that gave rise to something called expert systems. This was the earlier days of KBE. Expert systems was a simple computer system which could solve problems, which otherwise it needed human people to do the calculations on the sheet and solve the design problems. So they replaced that with computer systems which could solve complex problems. And that, when it started maturing, that gave rise to knowledge based engineering. Now, knowledge-based engineering is a complete knowledge-based systems which answers the complex situations, and in absence of that, it would need human efforts to do it. It would need human experts and human efforts to have done that. So, expert systems, they matured enough, and then KBE encapsulated AI plus the traditional design processes, the design knowledge what engineers possess, into a structured software code which could answer the design, the complex design. The design of industry is quite complex. It's not as simple as what we read in the textbooks or what we solve in the textbooks. Each product has a very complex design rule, design process, their own empirical codes, their own experimental codes, empirical also, experimental also, and their own knowledge, as I told in the beginning, that their own physics, the physics what the company has developed over the years. So to capture all that into a computer system is what KBE is all about. So this is a bit of a shift from how it all started in the traditional CAD and simulation world. In the When actually CAD started a few decades back, it started with drafting, 2D drafting. We used to have these mini drafters, have the design on the mini drafters, give it to the shop floor people. They could understand the drawing and manufacture the components according to those drawings. Slowly, that was replaced by 2D softwares, 3D softwares, wherein we had basic modeling, basic geometry creation on the software. Instead of creating geometry on the drafter using that big A4, A0, A1 sheets, that shifted to computers. It had simple mathematic rules. It was mainly dealing with linear systems. Now, if you come to modern CAD and simulation softwares, they are very complex and very comprehensive packages all around in the industry. You speak of softwares like NX, softwares like Katia, softwares like ProE, softwares like ANSYS, softwares like Abacus. So they completely replicate the physical form of a product on the computer. So that started with 3D model, parametric design, embedded rules to understand the complexities and nuances of the system, non-linear system, because nothing in this universe to design especially is linear. Everything has a set of non-linearity, and they started embedding machine learning, statistics, artificial intelligence into this 3D modeling and simulation also. So, KBE is again a collaboration of cross functional domain experts, and they come together through a computer system, and that computer system can be used to optimize the solutions what we deliver as products. As solutions we deliver products, right? Product is a solution for a specific problem, and to come up with that product we have a computer system, and that computer system is made by a team of cross functional experts. So to make that computer system you need experts who know the domain knowledge, who know the sensitivities of the system, the science of the system. You need people who know how to translate that physics or that science into a computer language. You know, the computer understands programming, it has their own languages. So you need a team of computer people, computer experts. You need a team of people who know how to package. Once you make a system, once you make a software, you have to also deliver that software to clients. You have to also deliver the software to clients who can use it easily. It has to be user friendly, easier to use for the people. So you need the people who can do the packaging. So that is where the DevOps team, you know, they come into the picture. So it's a combination of a lot of cross functional experts to make a structured system, computer system, which can be ultimately used by the product development or the design engineers. So this came about as a part of the digitization ecosystem. We hear this word digitization or shifting left in companies, right? So this KBE came about as one part of the big digitization ecosystem. The ultimate goal of any KBE system is to capture the best design practices, which only human beings know. By the way, these design practices are not there in any textbook. They are not there in any manual. They are not there in any research paper. So this design practices and engineering expertise is obtained by years of hands-on uh, work on those products, by knowing the sensitivities of those products, uh, by knowing the trivial uh, you know, the factors of those products, and then to capture all those small things, the best design rules, and then capture that into a corporate knowledge base. So when this comes in, when this KBE system is established, even if the person who has the knowledge is not there in the company anymore, his knowledge is secure in that corporate knowledge base. So that is the ultimate goal of the KBE system. Now, how does it work? So any product we design, we take into consideration four things. One is the designability. So do we know how to design a product? People come sit together and think, do we know how we want to come up with this product? Do we know how to first design it? Okay, now the we know how to design it. Second is, do we know how to manufacture it? Because manufacturing is a whole science by itself, is a whole system by itself. Lot of technological advancements, lot of things which can be designed but cannot be manufactured. So you always you know, hear this term design to manufacture, D2M. We always design to manufacture, because whatever we can design need not be manufactured. It cannot be practical, it cannot be cost effective, it cannot be made by human beings. You know, design engineers, they do something on the sheet of paper or on computer, they send it to the shop floor. The shop floor people tell we cannot manufacture it. So while designing, it's really important also to have the knowledge of the manufacturing process of that particular product. So you can design, you can manufacture. Now can you sell it? Because at the end of the day, it's all about you make products to sell your products. If your product is not being sold in the market, then there is no point making that product in the first place. And then once you sell it also, you have to make profit out of that product. We sell it cost to cost, there is no help for the company cannot progress, the organization cannot progress. So at the end of the day, you have to make money out of it, you have to make profit out of it. So these are the four factors based on which a product is actually come into the market. Now if you come to KBE, it captures all these four factors. It captures the design rules, relationships, captures the manufacturing limitations, capacities. It also, we have the cost models, we have the market models to capture the pulse of the market, and it also knows the cost constraints. This image, what you see here, so this is a typical workflow of any KBE system. This is the user who ultimately uses the KBE system, and the user is they are typically design engineers who work on modeling, who work on simulation. Instead of doing the simulation and modeling with their own hands, with their own you know, the mouse and keyboard, they use this KBE system. So it has a user interface through which the user can actually interact with the KBE application. And this knowledge base is the heart of any KBE system. It has got all the knowledge about that particular process, or that particular product. For example, in the next slides, you will see gear design. Gear design is a complex thing, and it has got a lot of geometric factors, uh, lot of mechanical factors. So all the knowledge pertaining to gears, all the limitations I told about, the empirical formula, the empirical factors, which is obtained by years and years of practice and hands-on. So all that is dumped into this knowledge base. Now this inference engine is a really important thing. The user interface gives a certain number of user inputs to create that product, and knowledge base has the capacity to create the product. Now, according to the user inputs, which knowledge base to create, which knowledge base to use, which equations to not use, which factors to use, which factors to not use, is basically decided by this inference engine. So this is sort of a middleware or middle layer, what you can tell, which talks to both the user interface and the kernel or the knowledge base, which has got all the science of the product. You can tell the physics, the intricacies, the limitations, everything. So this is how a KBE system is designed. It will be more clear when we see a couple of examples in the upcoming slides. Now, if you see these comparison earlier, when we had only a traditional engineering approach where people used to use CAD and drafting for design, and then send it to manufacturing, and then the manufacturing people used to send it back again to design to make changes. So this used to happen in the traditional engineering approach. We had this routine work of about 70%. 70% used to be routine work, and 30% of the time the engineers used to get to have the creative, to actually think creatively, to come up with innovative tools, methods, to come up with innovative ways of product development. They had about 30% of time. Now when KBE kicked in, it reduced the cycle of the routine time to about from 70% to about 30%. It increased the time engineers spend on creative tasks, and plus it saved time. And literally, I'm not exaggerating this, it literally saves time from days to minutes. It saves times from, for example, to design a product. We have, let's take the example of gear again. To design a gear without any KBE system takes hours. Takes 10 to anything between 10 to 12 hours for a medium level expertise of a design engineer to properly make a model of it, to design it with all the rules and all that. Now in KBE system, you just have to put in the inputs and see for yourself on the screen. It designs the product for you in less than 1 minute, less than 2 minutes. uh, Again, if you have a good system, good processor, it can be faster. So, how does it work? KBE lifecycle, you identify what has to be the KBE application. Because in the product development lifecycle, you have lot of steps. You have concept generation, you have designs, and then you have the modeling. You do the modeling or the design done on CAD softwares. Now, in CAD softwares, there are certain tasks which are repetitive. For example, you work on certain models. You have to create, for example, 100 models of the same kind. So these can be automated, or in these we can apply knowledge-based engineering to reduce the redundant work. So first you have to identify again, and then you'll have simulation works. And in simulation works also, you have three things. You have pre-processing, you have solving, and then you have post-processing. In pre-processing, you have meshing and all that. We have softwares, automatic mesh generation. Again, you have to identify. So the whole point here is to identify what can be a good candidate, what process can be a good candidate to apply knowledge-based engineering. Not everything can be applied with KBE. You have to first identify and then rationalize. So, why is this really needed? Why this should be created as a knowledge-based engineering? How much time it is saving? How many users of this processes are there? So if we save, say, 5 minutes for each user, how much time will be saving? And that translates to how much of money. So all these whys and hows, ifs and buts have to be done. And then consolidate, finalize the requirements, design, software architecture, and cost. implement, actually sit and create the tool, code the tool, and test it, extensive testing, test it to see, to make sure that it's giving the same result and same accuracy as what you had, as what you would have got if you had done it manually, right? And then you create a package of, CAD tools have a lot of geometrical dependencies, lot of physical dependencies. So create a package of all these dependencies in order that people with no background of programming or no background of computer science can actually use it. And then you deploy it on the user environment, user systems, on the customer, and train the people how to use it first. Make the people appreciate it, tell the advantages of it, tell how much time it saves, and then train the people on how to use it. Train the design engineers on how to actually make use of this efficiently. So this, if you see in the traditional CAD, in the traditional product development, you have a linear cost. As the time to create more complex time, to create more complex designs, the design cost keep on increasing. But in the but for the knowledge based systems, the initial cost is high, because this is where you actually finalize, do the software requirement, involve multidisciplinary people, involve mechanical engineers or the domain experts. It can be mechanical, civil, electrical, electronics engineers, and then involve computer science people to actually do the coding, or do the cross training, train computer science people to understand the mechanical part of it, or train mechanical, electrical, civil people to do the coding. So all these involves a bit of high cost, and then over time, if you see, the cost of design comes down. The cost of design comes down. A few applications of how it can be used. One is to automate the routine tasks, as I told. For example, you have a plate and you have to create 100 holes on that plate. Okay, for some applications you have a lot of especially for the stamping kind of applications, you have a plate and you have to create 100 holes. Now in the traditional CAD, you can actually go to the 100 places, click on the command to create a circle, a hole, give the dimensions and all, and create 100 holes by yourself. Otherwise, create a small software KBE program, wherein you just specify how many number of holes you want, and what should be the distance between each hole, and click on OK, and just see for yourself 100 holes getting created. So this is called automation of your CAD processes. So this is one of the applications of KBE. Second is your customization also. When you get softwares from big software vendors, you get NX, you get Katia, your company buys it, your company procures those licenses, because all these softwares are highly, they are costly, and they come with a license, and they come with a cost. But you need some capabilities in that software according to your product, because the companies which make the software, they keep in mind the general industry and make the software. Okay, you will need to customize that software. You will need to add few commands, add few processes to suit your company, to suit your processes. For example, I was working in a tire manufacturing company a couple of for 4 years, for 4 years. So we had to buy softwares from the big software vendors, and to create, I request everybody to please keep your mic on mute, for the convenience of everyone. Thank you. uh, when we used to buy the products, from software products from the companies, so we needed some commands or some things to be specific for tire geometry. For example, to create a tire, we did not have any, to create a tire geometry, we did not have any command, we did not have any method in that software. So what we did, we put our engineers, some of our engineers, to create that command, because each of these softwares, they keep some customization uh, areas open, wherein their software can be customized and used as per the user requirement. Okay, so the second area is to customize. The third area, what is still niche now, it is still under development. A lot of research is going on in this. Not much of industrial applications in this, is data driven simulation. Data driven simulation, we are all used to traditional simulation, wherein we have, uh, the traditional FEA and CFD simulations. We discretize the geometry, apply loads on it, apply the boundary condition on it, and then send it to the solvers. The solvers are highly mathematical partial differential equations which are performed on HPC clusters. And then it takes huge time, to solve one model. To solve, I was going across. I was working on one car model, a crash test for a car model. So a crash test for a car model, it has got around 2 million discretized nodes. 2 million is 20 lakhs. 20 lakh discretized nodes, and to solve each of that on HPC clusters used to take days together, 4 days, 5 days, right? So to minimize that time, we employ data-driven concepts. We use part of machine learning, uh, and some AI, this machine learning algorithms, to ease or to enable the simulation to run faster. So that will rely less on the physical equations, but will rely more on the data and the correlation of the data and all that. So that is what the data-driven engineering, or data-driven simulation it's called as. So that's an upcoming area of this KBE. And then of course you have simulation models, is what you have, these FEA models and CAE models. You also have functional models. Your If you see the softwares like IPG, car maker, car sim and all, they are into functional modeling. They simulate the behavior of a car when it takes a turn, behavior of a car when it actually brakes, behavior of a car when it undergoes a wet road.
That happens. I was expecting you to have that follow up question. मैं बताऊंगा. That depends on your problem. Okay.
I request everybody to keep yourself on mute, please.
This is what you mean, right?
All right. So these are a few applications of knowledge-based engineering, a few case studies. I have got three case studies, for one for simulation, one for CAD, and then for other applications like civil engineering, electronics, and stuff. So this is a case study. What we developed, we had worked on this particular software to create an automated tool for end-to-end simulation. Now, if you see this particular image over here, a car and some poles around that car, is the setup to test the noise of the car, exterior noise of the car by experiments. Okay, exterior noise by experiments. This is performed in highly controlled environments in specific labs, government labs in India, and a very few private companies have this facility because it comes at a very huge cost. So, to test how much noise comes out of that car, you have to have this track, bit of a particular road, and you have to have, these poles are all microphones. Okay, you have to keep these many microphones, and then drive the car at a particular speed. And we have a government standard to test this car. It's I think it's published by the Ministry of Road Transport. It's called Automotive Industry Standards, AIS. So AIS 152, 142, these are all the standards to test the noise of the car. So this can be experimentally performed, and if you have to change the microphone position, if you have to change the speed of the car, all that has to be done iteratively. For example, at once you can only test the noise only for one setup. If you have to change the speed, you have to again change the speed, perform the test again. So it's iterative process, more costly, takes a lot of time. This test takes days together, typically days together. Now what we did was replicated this test on a computer. Replicated this test on a computer. So this, what you see, this is a discretized model of a car. You see these small squares. We divide the cars into small squares, and then we come up with this particular meshing. Discretization is called meshing. Okay, discretization is called meshing, and then we come up with these softwares, and then the software replicates this noise. Now the advantage of that is, if we have to change the microphone level, one click can do that. If we have to change the speed of the car at which the testing is being happened, one click of a mouse can do that, because it's all software based, and just changing the user interface from say 60 kmph to 80 kmph, we can do that. But if you have to do it physically, you had to do it you had to actually drive the car at 80 kmph again, and change the microphone positions physically to test your different things. So this is how it helps to reduce the model time, reduce the cost to company. Multiple test cases, as I told you, can be handled in this, and it also accounts for the physics. These simulation models, what we have come up with, these also take into account the physics of the sound, the physics of noise, in order to give realistic results. Of course, we will have some error. Uh, every simulation you do, every virtual prototyping you do, definitely has some error, but those are engineering accepted engineering errors. Okay, so which will not affect the performance of the product on the whole. Now, the second application is the gear application. So this is the gear what you create, and this is the application. This is the knowledge-based application, and this is the user interface (UI) of that application. So if you don't have this application, the user has to do it manually. Create this circle manually, create the gear teeth manually. Now again, it is a redundant work. Once you create one gear teeth, to create the other gear teeth are all redundant work. It does not require any engineering expertise to do that. It's just a waste of time for the engineers, but it has to be accurate. If you don't have it accurately, manufacturing will not be good. So in order to address all these questions, the we came up with an application to actually create these gears and these get it automatically. All the user has to do is give these inputs and click on OK, this green button, and see for himself how it all works. So I have around 30-second video for this. Let's go through the video. You can actually see how this gear is working, how the creation of this gear is working. So this you see is the user interface, which captures all the parameters. You have the addendum, the radial addendum. These are all the physics behind which the gear is designed. The number of teeth you want, the pitch of the teeth, the width, and everything. All right, so I hope you saw how that gear got created automatically and how those teeth got generated on that surface automatically. So to have done that manually would have taken a lot of time. Plus, it's prone to errors also. The distance between the teeth should be only this much. If it is more than 1 mm, if it is offset by 2-3 mm, it creates problems for the manufacturing. So this is how it addresses this redundant work problem. And then we've got something called functional modeling. Okay, so this is a simple theoretical equation to calculate the power of an engine. Okay, the power is based on your speed and your torque. T is the torque of the engine, and then torque is again based on this force uh, into the radius of the drum, right? And then again, this force is composed of three factors. One is the rolling resistance due to tires. Second is the gradient, the slope on which your car could drive, and the aerodynamic forces. When you drive your car at more than 80 kmph, you have the opposite effect of the air. The air blocks the movement of your car, so that is the called the aerodynamic effect. And again, these are all dependent on so many things. The RR is dependent, is a factor of velocity or load or x and y coordinates and all that. Again, aerodynamic factor is again a function or dependent on shape, viscosity, and lot of other factors. Now, the advantage of these kind of simulation models, computer based simulation models, is if you have to see what effect your viscosity has on your torque, you can just change one value of viscosity and run the simulation. It will give you a different value of torque. So this is how you can do the plotting and see the comparison and see the effect of one parameter on the other parameter. If you had to do this manually, earlier to the simulation models, this was all done manually using calculators and all, but it does not give a realistic feeling to an engineer to take decisions, to actually take engineering decisions. This does not give a good platform. But these kind of simulation models, this is a simple code which can be done in Python and make some plots. Okay, so this can be used to do some comparative studies. The effect of, you keep all the factors constant, just vary the velocity and see what effect velocity change has on the torque. Okay, so all that things, all these studies, comparative studies, can be done to come up with more efficient product development. Now a few examples on how we so all these examples till now were for mechanical oriented products, mechanical engineering. Now we've got a few examples for civil engineering and electronics also. Okay, this concept of staircase, the design of staircase again can be automated. And we had a tool, we have this SDST tool, to which was developed by a set of people, as a research tool, mainly to expedite or to improve the time for the staircase design process. Again, you have one tool to inspect the room air supply and to extract the, it's mainly dealing with the MEP systems and AC and ventilation systems and all. Again, one tool to study how it all impacts the design of that particular AC and all that. Again, in electronics, you have these algorithms, like we've got ECUs, electronic control units, which actually in every car nowadays we have ECUs, and ECUs are nothing but a storage of your science. ECUs are nothing but storage of your science, and that are developed keeping into account your intricacies and your small changes to a car, and how varying one factor can affect the other factor and all that. So this is how this knowledge based engineering is embedded into these ECUs. And that ECU is again a part of each system, because you see here every part of the car is connected to an ECU. You've got the electronic control unit, again we've got tire, in tire you've got these sensors, and again it has got this ABS, anti-locking brake system. Again, ABS is nothing but an algorithm or a set of equations and some logic to actually tell the car when to brake, when not to brake, how much to brake, and all that. So again, this knowledge is embedded into these cars through these KBE systems. If you come to the technology landscape, what do you need? What technologies you need to start off some work on KBE? Is these on the top you see software programming technologies, and in the bottom, in the second half of the slide, you see these CAD and simulation softwares. Okay, now the idea is to pick one from top, pick one from bottom, combine it, and that forms your KBE system. Pick one from the top, pick one from the bottom, combine both, and that will form your KBE system. For example, you can take up C++, combine it with CATIA, Siemens, ANSYS, and start to program your CATIA, Siemens, ANSYS, or whatever softwares in C++, and that will be your KBE system. You can pick up, instead of C++, take up Python, VB.NET. This is a technology called CAA, which is very specific to CATIA and Dassault Systems product. Again, NX Open is again very specific to NX. Again, you can take up MATLAB. You can call MATLAB from your ANSYS. You can call MATLAB from your Siemens, and all these are famous product development softwares in the industry. You can take up any of this products and then take up one of the programming languages, combine both, and you can start making your small KBE systems. Okay, how do you make a career in KBE? Again, it is a combination of two skills. One is your software engineering skills, wherein we have C++, Python, architecture,
Ba- Rumah MT. Lehe mama ha.
Python, And on the other hand, you've got mechanical systems, understanding of physics, understanding of CAD, understanding of computer aided simulations, engineering, manufacturing. You combine both skills, and there you are, you become a KBE engineer. You start to develop these KBE systems. Again, on the research perspective, if you see, you've got this mathematical modeling. You can develop your custom modules. We have this ParaPi. ParaPy is a KBE module developed. It's a module in Python. It's a package in Python. Like we have famous packages like that. It's a package in Python which was developed by students of TU Delft. TU Delft is a university in Netherlands. Aerospace engineering students, they developed this ParaPy module to automate the uh, design of airplane wings, to automate the design of airplane wings. This was not industrialized. They developed it as part of their theses and research work. But you can develop
Okay.
these kind of modules and come up with research papers
Hmm?
and stuff, right? So a summary for this: it's a very efficient
Okay.
method
Start.
of product development, very efficient process with a wide horizon of
Huh?
applications. Very
Uh-uh.
promising career
जल्दी उठ जा
opportunities.
साहिद.
Typically it's very good for people who have worked typically on traditional CAD
हाँ
for
इसका.
5, 6, 10 years,
बादल कुछ
and
गया.
they have. I request everybody to keep yourself on mute, please.
हाँ सो लगती है चिड़िंगी ना कहीं.
Thank you. So I was telling, this is a very promising career prospects for people who are working on traditional simulation and CAD, to learn a little bit of programming, come on the back end side of how these softwares are made, uh, because they have very good hands on as a user, as a designer. They have a very good hands on experience. Now they can come at the back end with some programming skills, and then they start to develop these softwares. So that will be, and the companies are actually employing two three kinds of companies employ. One is the OEMs, the companies which actually make products, automotive OEMs, aerospace OEMs. So they buy the products from software vendors, and they have to customize. To customize, they need KBE people. Second is service based companies, because service based companies get products from these big OEMs and tier 1 tier 2 suppliers, and then they deliver products to them. Third is the software vendors itself. Companies like MathWorks, companies like Ansys, companies like Dassault, companies like these kind of companies, they need people with programming and mechanical, or the people who are experts in domain. So a wide range of opportunities, also a good technological landscape, and also good research opportunities, because it's a very upcoming and a new area. A lot of prospects for research. It has come the other way around. It came about first in the industry as a need of the industry, and then now people are still slowly taking up research based activities on this. People are doing theses, PhDs on these kind of on these kind of works, right? So that's all from my side. I hope the session was interesting and engaging to you. If you have any questions, we can surely take it up. You can either unmute yourself one at a time and ask questions, or let's see if we have some questions uh, on the chat box. Yeah, we don't have questions on the chat box, but if you have some questions, um, you can ask your questions by unmuting yourself.
Thank you, Abdullah bhai. So, do we have any
Thank you.
questions from the audience? Anyone wants to discuss anything?
Yeah, if we don't have any questions, I think we can wind up this session for today. Thanks a lot. Thanks a lot for attending. Thank you, Dr. Saib Sam.
Jazakallah, Abdullah bhai. Thanks a
Right.
lot for this interesting session.
Shukran.
Yeah, we have
Jazakallah
one
khair.
we have one question on the course certification. Yes, we have some institute called like PLM Coach and CAD Customization Coach. I'm just typing it out here. PLM Coach is a very what do you tell? It's I'll do it for everyone in the meeting. PLM Coach is a very famous vendor to provide these kind of certifications and trainings on these institutes on these kind of subjects. You can contact them. They are based in big cities. They offer remote courses also. But I suggest it if you're really interested, go through the organization because they'll be more interested to do it through your organization. You can do it individually also, but I suggest it to do it with your like through your organization.
Jazakallah khairan. Thank you.
Jazakallah. Assalamu alaikum.
Walaikum salam, jazakallahu khair.
Okay, Jazakumullah khair. Assalamu alaikum.